Okay, in this lecture we're going to talk about lateral stress. Okay, so we talked about vertical stress before. In this lecture we're going to talk about lateral stresses in soil. Okay, now before we begin, let's just review a few things. First, we recognize that stress acts at a point on a plane. Okay? So this is not only for soil, but for any other material. Okay? We also recognize that for soil, for the case of soil and geotechnical engineering, there are geostatic stresses. Okay? There are induced stresses and also dynamic, but we are concerned in this course with geostatic stresses. Okay? Now, in the case of vertical stress, we said that if we find the vertical total stress at a point and we subtract the pore pressure, that is the pore water pressure at that point, we get the effective stress at that point. Okay, in this case I'm writing the letter V for vertical stresses because those were the ones that we calculated, right? And so clearly pressure has no direction because it has all the directions actually. Right? It's a stress that acts the same in all directions. This is the total stress vertical, effective stress in the, that is vertical, right? Both these stresses, these sigmas, act on the horizontal plane at the point in question. This is the stress that the particles feel at that point on that plane, on the horizontal plane, right? And this is the stress that both the particles and the water feel. So this one plus this one is this one. Okay? So we had a situation, for example, where we had, three layers, 1, 2, 3. Water table might be here in the second one, and let's say we have a point here, right? So we said to be able to find these three geostatic stresses at this point, we need to consider what's above the point. For the case of U, we consider the water above the point. And for the case of sigma V and sigma V prime, we consider the soil above the point. Right? And then we do the calculations we had before to calculate, to get these three parameters, right? We first calculate this one, then this one, and then finally this one. You can calculate the U before you calculate this one, the total stress, but typically it's in this order. Okay, so if we look at this example here, if we draw this point in the humanoid way so that we can understand, or we can basically draw it. Remember that it has no size, but we actually draw it as a little square to be able to simplify our lives in terms of looking at the point, right? We said that the horizontal plane is this one, and the vertical stress, let's say we can choose which one we want to draw, right? There's actually two of them. So let's say we want to draw the vertical effective stress. Okay, so the vertical effective stress acts on the horizontal plane at this point. Remember, the point is this whole thing. Okay, that is this under the microscope basically. So we have our vertical effective stress acting on the horizontal plane. Now, the next question, which is the topic of this lecture here, is what is the stress that acts on the vertical plane? Okay, so you can see this point here. Let's draw it a little bit bigger here, not as big as that one, but let's say in between. So that plane, which is a horizontal plane, is that one, right? And the vertical stress acts like this. But there's also a vertical plane, this one. And the vertical plane has the horizontal stress acting on it. So we put an H, and because we are talking about vertical effective stresses, we should just, for the sake of consistency, we should have the horizontal effective stress here acting on the vertical plane. Okay, so the question is, knowing how to calculate this already, these three, how can we calculate that one? Okay, now you might be asking yourself, well, why is it that we want to calculate all these stresses at a point? Well, we need to calculate, for example, vertical effective stresses when we design foundations. Okay, foundation systems for structures. We need to determine horizontal stresses, for example, when we design retaining walls. Okay, so the design of geosystems involves the calculation, heavy calculation of stresses in soil. Okay, so this is part of the line of work that we have to follow. So the question is, how do we find the horizontal geostresses or geostatic stresses? Okay, we know how to find the vertical ones, right? That we did before. Here we are going to, or it's in another lecture, right? But here we're going to determine how to obtain the horizontal geostatic stresses, both this one and this one. Now you may say, what about the U? Well, the U is a pressure. So I keep on saying this, right? The U is a pressure, so it has no direction that is relevant. It has all the directions actually. So we don't have to, once we calculate U is just one number for any direction because it's the same stress for every direction. Okay, so we're essentially talking about the sigmas. Now you may be asking yourself also, well, what about the taus? We haven't talked about the taus that act at this point, for example, right? And that will come later. And you'll see later on how we calculate those taus. Okay, so here's the horizontal total stress. Here's the horizontal effective stress, in this case actually drawn acting at the point on the vertical plane. Now to determine the horizontal stresses, we need to know the value of the parameter K. Okay, parameter K is, this parameter is called the lateral stress coefficient. Okay, this K, the lateral stress coefficient, basically relates the vertical effective stress to the horizontal effective stress. It's a soil parameter, okay? And so the definition is this. It is the horizontal effective stress over the vertical effective stress at a point, of course, because stress acts at a point. Okay? Now, clearly, if you know how to calculate this, which you do, and you are given or know this value, then you can basically say this times this is equal to that. And essentially it's as simple as that. Okay? So if you are designing a wall, for example, a retaining wall, or if you're designing a foundation or whatever, and you need to determine this stress, you are going to be given, in quotes, a value of K. Now, of course, in nature, in real life, nothing is given. We have to measure things, right? So the value of K is sometimes measured in situ, that is in the site, sometimes measured in the lab, sometimes it is estimated, right? Typically, it varies between 0.4 to 0.6, something like that. We typically assume a value of 0.5 if we want to do simple calculations or back of the envelope type of calculations, okay? But it's a parameter that must be measured so that we can actually use it to determine the horizontal stress once we know the vertical stress. Effective, huh? Do not forget the effectives. That is the fact that this is a ratio of effective stresses. If you mess up and you forget that this is effective stress and this is an effective stress, and you put total stress and total stress, you will get the whole thing wrong. Okay? You must make sure that you realize that this is the definition. Do not mess it up. Back to the K, the lateral stress coefficient must be measured so we can use it, right? And it's actually one of the most difficult parameters to measure in soil mechanics and geotechnical engineering, but we can get some estimates and then use it to determine the horizontal effective stress. Okay, so very simple. If you have, I'm going to do a little example over here. Let's say that we have a site. Okay, and here's a point. Let's say the water table is the ground surface. This is, let's say this is 6 meters. Okay, this is point A, and the rock is down here. Okay. Oops. So this is a sand with gamma is equal to 20, and K is given as 0.5. Okay, so before we continue, notice that the whole layer is assigned a value of K. Okay, now this may not be the actual truth in the site or at the site in nature, right? The K can actually vary with depth. So K can be up here, could be like, 0.6, then over here it could be 0.4, then down here it could be 0.5, and then 0.6 again, etc. Right? But typically in geotech, in engineering, we assign an average value of K to a layer. Okay, so a layer will have a gamma, a layer will have a K value, a layer will have a, for example, a strength value, and that is of course okay if the parameters don't vary that much, right? So for example, if this sand, just to continue here with this variation stuff, if this sand layer is made of the same grains, but up here it's loose and down here is dense, so let's say that up here the E is high, the void ratio, and then down here the E is low, then what we could do in engineering, we could say the following. We could say, okay, we know that this whole layer is made of the same type of sand, but we know that the top is loose and the bottom is dense. So let's assume it's basically two types of sand. This one has a high void ratio and this one has a low void ratio. Clearly, the fact that this has a high void ratio would be reflected in the gamma. So the gamma up here would be less than this one, let's say down here. Okay? So, but for the sake of this problem, and basically generally most cases in geotech practice, we assume a gamma for a layer, right? So here's K, here's a gamma, right? And we're going to find the geostresses, or sorry, the geostatic stresses at this point. What are the geostatic stresses? Sigma H, sigma V, U, sigma H prime, and sigma V prime. Okay? So, let's begin. In fact, what I'm going to do is I'm going to use another page. So, okay. So, let's see. We begin with the calculation of sigma V, right? So here's point A. So the vertical total stress at point A is equal to what? Well, here's the point, right? There's 6 meters of saturated soil above the point. So 6 times 20, 120 kPa. Alright? U. Here's the point. There's 6 meters of water above the point. 6 meters of water. This is about 60, right? Alright. Now, notice that the calculation of U has nothing to do with the soil, right? There's no soil parameter here. It's gamma water and the pressure head. Okay, some people, for some reason, mess this up and they think that U is dependent on this 20 or something. No. U is dependent only on water. Okay? Now, sigma vertical A, at A, right? Prime. The effective stress is the total minus the pore pressure. So 120 minus 60, in this case is 60, right? Alright. Now, let's do the the horizontal stresses over here. We are given that K is 0.5, right? We know that K is equal to sigma H prime over sigma V prime. That's the definition. So sigma H prime is therefore at point A, is therefore 0.5, which is K, times sigma V, and sigma V is 60. So this is 30 kPa. So it's very simple if, of course, you are given this K. Now it's another story to measure this K, but let's say that we have hired somebody to measure it, we're designing, we're calculating this value, this is the value that we will use, right? Because we are given it, this is given to us by, for example, the lab that we hired. Okay, now, the last one we need is sigma H at A, total stress. Now, what we need to do here is make sure that we don't make the mistake that many people make, which is to assume that we can multiply sigma VA times 0.5 and get sigma HA. That doesn't work. Why? Because K is a ratio of effective stresses, it's not a ratio of total stresses. To get this value, we need to realize what Terzaghi said. Terzaghi said sigma is equal to sigma prime plus U, right? The effective stress principle, what we used here, right? To get this, we said this minus this is equal to that, right? This minus that equals this. So here, what we do is the following. We say, look, on the vertical plane, there is a sigma H, right? The vertical plane at point A, there's a sigma H, this one right here, right? That acts at the point, and that's this one. Now, that's a total stress, the total horizontal stress that acts at the point on the vertical plane. Well, in this case like that, right? The vertical plane. So the plane is all this, right? So we have this, we have what the particles are feeling laterally, horizontally, that's this. And we also have U, which is this. So, remember, the water is feeling the same pressure, that is the same stress, in every direction. Laterally, vertically, however it is, it's feeling 60. That's what the water feels. Horizontally, or laterally, the particles are feeling 30 at that point. So, horizontally, the particles and the water, both of them, total, are feeling what the particles are feeling laterally plus what the water is feeling laterally, right? So this is equal to what the particles feel laterally plus what the water feels laterally and in every direction, 60. So this is 90 kPa. Okay? So this is sigma H A. So now we have all of them. We have these 3, 4, and 5. Notice that if you had made the mistake of multiplying this by 0.5 to get that, which is a mistake, right? To multiply this by 0.5 to get this is a mistake. You would have said, oh, 120 times 0.5, that's 60, right? So you would have gotten sigma HA equal to 60, and that's wrong. It's clearly wrong because it's equal to 90. Okay, so make sure that when you find this value, you're going to find it using Terzaghi's effective stress principle.